A square matrix A is called diagonalizable when it's similar to a diagonal matrix. This means that D can be written as P inverse AP, where P is an invertible matrix and D is diagonal. But these aren't just any matrices. D has the eigenvalues of A along the diagonal. This can also be written as diag and then the eigenvalues. And matrix P has the corresponding eigenvectors of these eigenvalues in the same order. Pause. What are eigenvalues and eigenvectors? Rather than just doing the calculations, let's try and understand what they actually are. If we start with the standard basis of R2, E1 and E2, where E1 is 1, 0 and E2 is 0, 1, remember that all linear transformations can be represented by a matrix. And to find the matrix of the transformation, we follow where the basis vectors end up. Let's say the vector 1, 0 becomes 3, 0, and the vector 0, 1 becomes 0, 2. This transformation scales the x direction by 3 and the y direction by 2. Let's pick another vector, say 1, 1, and see what happens. 1, 1, when transformed, becomes 3, 2. If we wanted an actual equation, we could do our matrix times xy, and we would get 3x, 2y. If we start down here, for example, at -1, -2, we would go to -3, -4. When we apply the transformation A, as you can see, most vectors are taken off of their span. They don't remain on that same line. The two vectors that do remain on their same line, or on the same span, are E1 and E2. They're just scaled, right? This is exactly the definition of eigenvectors. After the linear transformation is applied, they stay in the same span. They could be scaled by some factor, but they stay on the same line. What's an eigenvalue? This is how much the eigenvectors are transformed. They might be scaled or compressed by a certain factor. Let's identify the eigenvectors and eigenvalues of this transformation. Our first eigenvector is 1, 0, and its eigenvalue, how much it was scaled by, is 3. The second eigenvector is 0, 1, and its eigenvalue is 2. So in this case, if we're trying to find A equals PD P inverse, P is our eigenvalues, and D has the eigenvectors along the diagonal in the same order. How do we find the eigenvectors and eigenvalues algebraically? The eigenvalues are the roots of the characteristic polynomial. Eigenvectors and eigenvalues have the property that our matrix A times an eigenvector is the same as the eigenvalue of that eigenvector multiplied by the eigenvector. It's scaled by whatever the eigenvalue is. Once we've identified our eigenvalues, we need to find x, the corresponding eigenvector. If we move A times the eigenvector to the opposite side, we'll end up with 0 equals lambda times x minus ax. Both terms have this x, so we can factor this out. But since lambda is just a scalar, we have to multiply it by the identity matrix. You'll notice that lambda I minus A is the same matrix, so you don't have to regenerate it, you can just reuse it. And this will be the coefficient matrix of the homogeneous system. If when we solve this system, we'll find the solution to the homogeneous system. For each eigenvalue, we have a corresponding eigenspace, which is by definition a vector x, which is in Rn, such that our matrix A times the eigenvalue is the same as the eigenvalue times this or these x's. The matrix A is diagonalizable when the eigenvectors are independent, or when Rn has a basis consisting of the eigenvectors of A. We can either have two cases. First of all, that the matrix has distinct or single eigenvalues with a multiplicity of 1. These correspond with an independent eigenvector. So the eigenspace would be the span of just one vector. Or we can have a multiplicity greater than 1. In this case, in order that A is diagonalizable, the dimension of the corresponding eigenspace must be equal to the multiplicity of the eigenvalue. If A is not diagonalizable, then this dimension would be less than the multiplicity. Lastly, this eigenspace is a subspace of Rn, and it cannot equal the zero vector. A basis of the eigenspace can be found by Gauss elimination on this homogeneous system. Diagonalizable matrices. Here are a few properties. If A is similar to B, and we have that A is diagonalizable, this is true if and only if B is also diagonalizable. This can be thought through pretty quickly. If A is similar to B, because we know this is symmetric, as similarity is an equivalence relation, we can rewrite this as B is similar to A. And if we say that A is similar to D, because this relationship is transitive, we can conclude that B is similar to D. We also have that if A is diagonalizable, A transposed, A inverse, and A to the exponent k are also diagonalizable. And I went over very similar proofs in my previous video. Is this matrix diagonalizable? And if so, find P, which is composed of the eigenvectors, where P inverse times A times P is the diagonal matrix. First, let's find the characteristic polynomial in order to identify the eigenvalues. This is the determinant of lambda times the identity matrix minus A. Instead of taking the 3 by 3 determinant directly, we can simplify, but keep in mind what happens to the determinant with row operations. We could switch row 1 and row 3, but when we switch, the determinant becomes negative. Next, we could factor out -1 from the first row, just so we get a +1 in the top left corner. This means that we'll have negative in front of the determinant. This becomes +1. Next, we can take row 2 plus 2 row 1, and row 3, because we want zeros under this leading 1, minus lambda minus 1 row 1. When we add or subtract multiples of another row, this doesn't change the determinant. In the second row, we'll get 0, lambda minus 6 plus 4, then minus 2 lambda, minus 2 plus 6. On the bottom, we get 0. Let's apply the negative sign in, so we get negative theta plus 1 times row 1, which is times 2, minus 2 theta, plus 2, and then plus 2 again, so plus 4. And lastly, what is negative theta minus 1 times row 1? We can factor out a -1 from this term. Then we'll get positive lambda minus 1 times lambda plus 1, which is lambda squared minus 1. -3 plus this. To simplify the second and the third row, let's factor. We can factor out lambda minus 2 from the second and the third row, so I'll say lambda minus 2 squared. And now why don't we take the determinant? We can expand along column 1. Let's calculate the 2 by 2 determinant. We get lambda plus 2 minus 4. So of course we can rewrite this as lambda minus 2 cubed. What is the eigenvalue? In this case, there's only one. Our eigenvalue is 2, and the multiplicity is 3. As we see, it has an exponent of 3. Next, we can plug this eigenvalue into this matrix, which is equivalent to lambda times the identity minus A. We can quickly reduce row 2 plus 2 row 1, and row 3 plus row 1. This eliminates the second and the third row, and we're left with two parameters, two non-leading columns. Remember, this is a homogeneous system, so we can write this as A plus 2B minus 3C equals 0. Let's solve for A. And our solution to the homogeneous system is B times what? How many B's does A have? -2, 1, 0. Plus C, we have 3 in A, 0 in B, 1 in C. And if we want to write this as a span, we could say the eigenspace of eigenvalue 2 for a matrix A is the span of these two eigenvectors. And since this dimension is less than the multiplicity of the eigenvalue, which is 3, we can conclude that A is not in fact diagonalizable.